This is day 16 of doing Leetcode 75. We're doing the kth largest element in an array, and we're given an integer array nums and an integer k. We have to return the kth largest element in the array. We have to note that it is the kth largest element in the sorted order, not the kth distinct element. So, and we're going to try to solve this problem without sorting the array before checking the kth largest value, because we could just sort it by maximum value, and then we can easily just grab that index to grab the kth largest element. So you can see here that if we want to find the second largest element, it's going to be 5 when we check the entire nums, or check on the entire array. And for example 2 here, even when you have duplicates, so you want to check the fourth largest element. So there's already 6, 5, and 4. 6, 5, 4. And that is because I think when we sort the array, I wonder why this returns 4 actually. Kth largest element. I think it's because these duplicates actually count, so we need to count them in our array as well. So, or in our count as well. So there's 6, 5, 5, and then 4. And we have to make sure to take that into account. Okay. So the way we can solve this is using something called a max heap, where we essentially are creating a complete binary tree, and the value of the root node has to be the largest among all the descendant nodes, and the same thing has to be done for its left and right subtree. So what a complete binary tree means is that if there's a root, if there's a node anywhere in the tree, it has to have a left node and a right node, or none. Okay, or neither left or right. So you see the first example is a max heap, because the 8, which is our root node, has a left and a right node child, and 7 has both a left and a right root child, but then 5, 4, and 6 are treated as leaf nodes, in which they don't have any left or right nodes. So this is still a valid max heap tree. 8 by itself is also valid because it has no left or right children, so it's just a leaf node. And this is a complete binary tree where every single 8 or 7, 7 and 6 are they have children, and they have left or right. They have left and right children. In 5, 4, 3, 2, or leaf nodes in this case. So these examples are not valid because if we place an 8 node, we have to have a right child. If we have the middle tree here, 7 has to have a left child. And for this one here, you can the largest must be among the descendant nodes. Every single value of a node needs to be larger amongst its descendants. So 4 and 7, 4 is not greater than 7, so this value violates the max heap property. Yeah. Okay, so the way that we can solve this is by thinking about how essentially we want to fill up our heap until we reach k, and every time that every time the size of our heap exceeds k, we want to pop the minimum value out of our heap, so that we can, in terms of space, we're keeping the space pretty constant by keeping it only at k, but we just keep inserting more elements by also getting rid of the smallest elements. So say that our heap right now like it had 3 and 2. Okay, so let's say that we're iterating through this nums. We have 1. We wanna so say that we've exceeded k at this point. So we went to 3, 2, and 1. So that means that we have so we have up to k now, and or we have k plus 1. So now we need to get rid of one of them to make it to be k. So we have 3, 2, 1. Say that we're like at the third element right now. So we're gonna get rid of 1 because that is the most minimal one. Say we add in 5, we're gonna get rid of the most minimal one, which is 2. Say we're gonna add in 6, we're gonna get rid of the minimal one, which is 3 in this case. And that's not representative of how the heap will look like. I'm just showing you an example in the terms of our nums array. Now we have 5, 4, or 5, 6, and then 4. And then we get rid of 4, and then we just select the second to largest one, which in this case would be 5. If it would be in the heap, it would look like something like this. So then we would choose nums of, or like say this is still nums. And I say that we're actually manipulating it, we'll just use nums of k. K is equal to like 2 right now. Like say we did like choose k minus 1, so we can choose element 5. Right, okay. So let's see. Yeah, okay, I think that should be okay. So we're gonna create our heap. And we're going to iterate through nums. And we're gonna push into the heap n into h, I believe. H and n if the length of the min heap, if the length of the heap. We're actually creating a min heap here, but you can also create it as a max heap. Just showing you how the min heap will look like, or the max heap will look like, so you get an idea of what a heap actually looks like. But the min heap here is actually useful because we're able to, it's easier to traverse through the tree to find the value that we want, right? So if the length of the heap is greater, if you want to create a max heap, all you have to do is add a minus, I believe, in the second element, or the second parameter, every time you're pushing in elements. If you want to create a min heap, you can just pass in the actual element itself. If it's greater than k, then we'll start popping the minimum value out of it. Okay, so we want to return h of k. There you go. And yeah, that should be that answer. And we can also check how the heap will look like over time too. So yeah, like we said, it was, and yeah, so what I said was we return h of k, but we actually should return h of 0 since we're creating a min heap instead, and we're storing it by like the first. So we're looking at that largest element, so we need to see like the 0th one will always be like k, so it'll be like a reverse order, right? So if we're looking for the third largest element, it's going to be in our heap, it's going to be the first index, which is 0. It's going to be like the third largest, then the second element is going to be the second largest, and the third index is going to be the third largest. So it'll be stored in that order, so we can always return the 0th element. So we showed how the heap will look like over time, and we're storing actually a min heap because it's easier, since all we need to do is return the 0th element. But technically, if we were to store a minus h and we return k minus 1, this would still work. I lied. Oh. I'm just trolling. Oh yeah. Oh, the reason why is because we would be popping the most minimal element, which would be like -6 and -5 if we were to look at example 1, so that cannot work. So you have to use a min heap in this case, yeah, to solve this problem. Okay, yeah, this is the solution to a problem.